two pieces, or maybe three, 2.5 pieces of information. The Arrhenius law and fitting data to Arrhenius law. I don't have slides, I will just scratch something on the screen. And second, how to operate this module for eigenstates that some of you may enjoy using. If I believe I have explained everything in the email, but I can try running it on help any of you to run on for your personal problem. So, and feel free to stop me. I'm just filling the gap. You do not need to listen to me. You can do projects as you understand them. So, Arrhenius law is needed as a way to inspect how the chemical reaction rate depends on temperature. And here is like how I would oppose the last statement if I would sit on the other side of the barricade. If you do have a working and reliable computational way to compute rate of reaction, why do we need Arrhenius law? And the answer is as follows. By computation, we do not have an equation. We do not have the universal answer. We get only several data points. And typically, we expect that one can interpolate and extrapolate away from these data points. So, Arrhenius law is serving to interpolate and extrapolate rate of the reaction as function of temperature. And it is believed to be useful and correct. And it is, since you had it in the freshman chemistry, it will be quite standard way to communicate to other chemists. To say, like, my data are fitted into Arrhenius law and provide this much of activation energy. For eigenstates, it's just an illustrative thing, and one can analyze dynamics. If you analyze it verbal, you can analyze it hypothetically, assuming that at any point of time and space, what you see is a certain superposition of eigenstate. And if your project uses temperature as a control parameter, or momentum as a control parameter, it may or may not be interesting to show eigenstate. But if you have electric field or energy offset as a control parameter, then the eigenstates will be different anytime you rerun the code. And it may create or remove some eigenstates from those. And again, feel free to stop and interrupt me anytime. I'm just doing what I believe is helpful, but I can do. So if you do have some reaction coordinate, you have the potential, and you do have various V1, V2, V3, then in order for we packet to overcome the barrier, the momentum square over 2, which declines kinetic energy and is proportional to the temperature. there is a conversion factor from between atomic mass and temperature. It defines whether the wave packet will pass through or will be bounced back from the barrier. And intuitively, if this kinetic energy is less than in this notations V2 minus V1, we can call it energy of barrier. Energy of barrier sometimes is different from activation energy. It is less than energy barrier. Then no reaction. Rate is zero. If kinetic energy is approximately equal to energy of barrier, then some reaction. And if kinetic energy is much bigger than energy of barrier, then Q is large, and it is vivid reaction, same as if there would be no barrier, same as it would be free space. But this little verbal explanation is too qualitative. You can make it better and be quantitative. So this the rate of reaction can be computed, right? You can rerun, make a set of different values of P naught, like table P naught starting from 0.1. In each, depending on the mass, the values are different. And then, of course, it corresponds to different values of temperature, and then one can compute the rate, either as a slope or in some versions of the code, it pops up as a number in the command line after you finish the code. You just hit the table. And there you run it like 10, 20 times, and there are points. These points can be fit just to learn the values of activation energy and the prefab. So I'm confident that you know it, and I'm just reminding you this stuff. So the ratio between activation energy and thermal energy defines whether reaction goes or does not. So if activation energy is smaller than KT, then e to the power 0. If it is smaller, then it is about 1, right? 0. And if it is either equal, then it will be e to the power -1. It will be like 1 divided by 2.7, so 1.3. And if activation energy is substantially bigger, then it will be e to the minus infinity, will be 0. This means now, mathematically, what can we do and how can we treat this stuff? What if you divide left and right by 8? And then take log natural log of both parts. So then logarithm of rate minus logarithm of this pre-constant equals minus activation energy over temperature. Right? One more step. So logarithm of height as function of temperature that can be computed equals logarithm of this pre-factor minus activation energy over T2. So suppose we do have in our table we have only two values: temperature 1, temperature 2, and then your MATLAB code gives you K of T1, K of T2. I'm declaring that this little table will be sufficient to find the value of activation energy. So if you plug in these values T1, T2 into the equation, you get K and K of T1 equals K capital minus A divided by C. And T2 equals F3 minus activation energy divided by KT2. Now we can subtract these two equations from each other. Right? And then on the left, we get N KT1 minus N KT2. On the right, we have this bulb will be cancelled. And then we will have minus E A over P 1 over T1 minus 1 over T2. Right?
So for mine, I keep my momentum constant.
The best way for you probably
So I kept it at 0. So for my temperature, since I would have a constant temperature, so down this to 0. So if my T1 is 0,
I think I would answer. And then relative color is to translate thoughts from types of features into videos. Arrhenius is not as important to the market, although it can be, in some sense, Marcus Pauling, that we have found in one that the data set support, is an extension of
this here, is looks exactly the same.
yeah, but we need to give more details. What is that? It's a GS function for organization.
And that is
That's correct. Yeah. So,
sure.
You're on the right. If you really want to enjoy the radio sport, you check it. It's not as important, but I will come at this more important stage. So depending on what the run is at least two temperatures for each energy cell, and then find what is the solution. Which will be activation energy as function of energy of cell between atoms. But it is kind of next stage of shining gold. The first thing is just to analyze how the rate depends on the energy of cell.
And for the rate depends on the energy of cell. Like in this graph, it doesn't really.
Okay.
Does that look correct?
So the numbers in between. Let's okay. If you read this graph, this way is supposed to
Log 2?
yes.
Okay. So ln of
Mhm. So this equation can be solved for activation energy, right? Okay. So if we keep activation energy here and then divide left and right by this factor, then we get N1 minus N2 divided by 1 over T1 minus 1 over T2 and multiplied by Boltzmann constant activation energy. So if one practices this equation in a short time, often one is getting some errors with the Boltzmann constant in atomic units or stuff like that. But the trend and graphs will be correct anyway. So I'll try to assist in the ability to fix all things. But if you just extract this number out of your two data points, it will be very interesting thing to compare this Bailey. And the expected result is that in this image, the activation energy will be lower than barrier height. So if you obtain this result, it will be really important scientific value. Activation energy by Arrhenius should be smaller than height of a barrier. few slides forward. So how to analyze this equation? How to wrap minds around it in a graphical form? So if one plots the data from our mini table, of k on y, and 1 over t, 1 over temperature on x, then the points from calculations will look approximately this way. And if one does more than 2, like 10 or 20, they, with some errors and deviations, they will be scattered approximately around one line. And then one can draw an average line and tell that slope of this line is activation energy. In real life chemistry, in complicated reactions, there are different ways. For example, it can be composed of 2 lines, different slope at some at different ranges. But approximately for in the first approach, it is a line. And basically what you do, you convert complicated reaction with a lot of parameters into just 2-dimensional line and slope. And it is standard way how chemists speak about reaction. Is it enough information to process the data? Yes.
How do we find the temperature? That different from T0, right?
So it is kinetic energy, right?
Okay.
And kinetic energy is Boltzmann constant times temperature.
Okay.
That's it. So you take this stuff, divide it by Boltzmann constant, and it will be your temperature. The only thing is to express Boltzmann constant in right units, in correct, in appropriate units. So if you, but I'll try to help. You can find it yourself. You can try to find it together. But even if something will be a little wrong with units, it will not affect the value of your work. Does that answer your question?
Yeah.
Okay. Anything else you need for going to productive stage?
Oh, and then so when it says that the answer equal, that is
Or it's on my slides or somewhere?
no. When you run the code, then it gives you AMS equals some value. That is your K value for the reaction.
We need to open it. Yeah, you share it.
Or
You mean the rate?
yeah.
I think it is. Just can you maybe so that you can do it through screen sharing. bring participants. I'll give the sharing privileges to everyone. Just host. Make host. Make candidate. Make host. Uh-huh.
So the thing needs to be very active.
Uh-huh. So I believe so, but for double check, let's open the code and scroll through the code. So let's find at the end of the book, or maybe after the end of the book. So it's, we are looking for K3 where it is defined. And if you cannot find it, oh, here. Okay. So what is AVE-PL3? If you bring up the images or just type, yeah, maybe figure, maybe figure 4. So it looks like the AVPL3 is the orange curve here. So the question is how to extract the rate out of this curve. Find what? Find, just repeat. Yes, but if it is not straight, find the slope. Yeah, it would make sense. So it raises from 0 to 0.25 in about 200 units. So 0.2 divided by 200 will be 1 to the minus 30. Let's look what is the value that it calls. Minus 2.8 to the minus 4, so maybe 3 times smaller than I have estimated. So it's not bad. You can do it by hand. But there are additional ways to assess the rate. So if you type figure, enter, and now plot this variable plot, bracket, AVEPL3, or yeah, AVEPL3, close bracket, enter. Or you can do, yeah, it's the same. They just, if you do 1 minus this one, it will be, if you do PR3. So if you, let's go back to your command line, arrow up, go to the beginning of, right after the opening bracket, type DIFF, open bracket, go to the end, close bracket, enter, look at the image. It's an easy fix. Let's go back to the command line. Arrow up. No, let's go back to the figure. I'm just checking. Okay. Sorry for the delay. Go back to the command line. Hit enter and type axis, AXIS, open bracket, open rectangular bracket, rectangular bracket. Yes, and type 2 space 400 space 0 space 0.01. Close rectangular bracket, close regular bracket. Okay, and let's go back to the image. Okay, let's go back once again. Arrow up. Let's fix. Let's make it go to the 0 and make it 0. 0. Let's make it minus 0.01. Enter. And let's check what happens with the figure. Okay, good. So derivative. What you did is a derivative, right? And the derivative is rate. So if you have population as function of time, you take derivative, you get rate. The only thing is the rate is not constant. It increases and then decreases. But you can take average value or maximum value, which will be like 0.002, quite close to what you put in this case root, right? So you can take this number, also record it. And I'm going, if you let me share, I'll show something in addition. So if you do have this population of the reactant as function of time, which goes from 0 to 1. One needs to find a rate. One way is to manually find a slope. Right? Another way is find micro slope, which will be p of t plus delta t minus p of t divided by delta t, which is just a very deep derivative, right? So rate is the derivative of population over time. There is one more thing, much more elegant, and it will work even if the line is not straight and behaves very strangely. And what I'm talking right now is applicable basically to everywhere. You can complete the project without this comment, but it just shows how calculation of the rate is working. So let's assume that it is zeroth order reaction, so that population of reactant is decreasing with rate k times t, and then since population of reactant plus population of product is 1, then population of the product of t will be 1 minus t minus pt. So suppose we assume that our numerical data, t here is time relevant temperature. We assume that our numerical data obey this trend, right? And the question is to find k, find k. So one way was to take derivative ddt p product will be k times e minus k times time, and if you take it at time 0, then it will be k. Right? But it may not always work because rate depends on time. Here is one additional trick. What if we integrate this thing? So, e minus rate times 10 equals 1 minus probability of product. Right? Not lying. Now let's integrate left and right over time. Then here we do have we need to d of t to make it easily integrable. And in order to make it possible, we divide it by k, right? Which we can remove upfront. Then we do need the time of reaction. It goes from time 0 to time infinity. Then exponential integral of exponential is exponential itself, right? Then we have e to the minus t, the value equated at values 0 and value infinity equals just repeating the same from 0 to infinity, 1 minus p of the product over time. And then and we do have 1 over k. So 1 over k e to the power minus infinity minus e to the power 0. What is e to the power infinity? 0. What is e to the power 0? 1. So we have minus 1 over k equals integral from 0 to infinity 1 minus p dt. And we can solve for k, which will be 1 divided by integral from 0 to infinity minus symbol 1 minus p dt. Make sense? Now let's. I'll stop sharing and Jared, please share your. I was not sharing; it was only on screen. Yeah, please share your screen and bring the definition of K3. So P1 is replaced by the nominator is more complicated, and I can comment on this. The equation that I was deriving was based that population changes from 0 to 1. If it changes in different range, then it needs to be scaled. And here it is scaled from first and last values. So the denominator is population at point n tau minus population at point 2. Slightly go from 0 because at 0 it makes spike for medical reasons. Then divide by summation of this AVEPL3 times tau, which is an integral over the population over time, right? So this thing is integration-based calculation of the reaction rate. Okay, so you may type it as an equation in your report and in maybe as a backup slide for your presentation. So if someone asks you, how did you compute it, you can, here it is. Did it address your question? Yeah. Are you equipped for productive cycle? Okay, yeah, let me know if there are more questions. So let me check if there are questions from, any special questions from Connor, Kennedy, and if there are no explicit, feel free to stop me. And if there are no questions, I will keep going to demonstrate or to discuss about the eigenstates. So Connor, do you have a microphone available?
Yeah.
Okay, excellent. Did you do you think eigenstates are needed for your project?
I do not right now. No.
Okay, then please keep going. I'll ask you again if there are questions as we have this meeting. And, let me check if Kennedy has microphone available. Kennedy? Okay, maybe microphone is not. Okay, do you have a hello? Do you have microphone available at your workplace?
Hi, yes, I do.
Okay, very good. So it could be reasonable to try eigenstates for your project, and if you feel comfortable, you may share your screen with MATLAB, and we'll browse through things, and I'll just check how things are going and suggest how to run eigenstates if you find it useful.
Okay.
Let me check if. Yeah. Okay.
This is the MATLAB I have now. Can you see it?
Yes, I can.
Oh, there. Okay.
Very good, very good. Okay. And right now you're sharing only one window with the code. Is it possible so that images, the figures will be seen as well? Like if you share the whole desktop rather than one window.
You want what? Sorry.
If you want the figures that are appearing when you run MATLAB. I'm going to suggest that we flip between figures and command line several times. like when I'm sharing screen, when I'm going to share screen, it asks whether I want to share the whole desktop or on the specific application. And,
You can't see my figures right now?
no, I can see only the command line and
Let me.
program. Now I see. Okay, very good, very good. Now I see the figure.
Oops.
It makes sense. Yes.
Yeah.
And I see some delays. It's normal. It's normal.
I don't know how to share all the figures at one time.
If you stop sharing and then start sharing over again, it will ask you which screen to share.
Okay.
And when you do it, one of the options will be to share the whole desktop, like all, like
Show all windows?
all windows. Yes.
Did that work?
Oh yes, absolutely.
Okay.
That's great. That's truly great. So let's.
The main one I need, right? The probability.
Yes, exactly. And for each run that you are doing, you may extract the rate out of this red curve.
Yes. Okay.
And in this case, maybe the slope will be the best. Slope only during the ascending part of the trajectory, because it goes later on, it stops going forward.
Right.
Do you have this module for integrated rate in your code?
I don't think so.
Okay. Jared, would you please copy paste this part and send it to the chat? K3 equals to blah blah blah, and copy it to the chat. That's fine. It was close. You got it? Okay. Yes. So Kennedy, if you consider to copy this statement from the chat, and
I just had the chat. I don't know.
you can paste it as a very last line of the code, and for the first, just go to the code, to the script, scroll to the end. And after everything, just paste the stuff from Java, which will be like line 339.
I don't see where the chat is.
Chat is
It says it's right here, but when I click on it, then it doesn't show up. It's on your screen, so maybe it's.
Maybe if you stop sharing, look for the chat once again, and then start sharing over again. Now it should be visible. So there is a Zoom control panel. It has unmute, stop video, security, participants, poll, share screen, reactions, and then for more, it has the chat.
So now you can't see mine, right?
Can you see your chat right now?
Yes, I can. I got it.
Yeah, just copy this statement from and Jared, and maybe start sharing so that we act cooperatively. Very good, very good. And let's go to the command line, this command window, the lowest window. Click there, put the marker lower, down, yes, even lower, below this line. Below, where the orange text are.
Oh.
Now click and type Control-C to stop, to interrupt the program. Control-C, and try to paste by Control-V to paste this statement. It works, it works. Maybe it will have some error because of specific of your program, but you can use it as a backup plan. So this case 3 will be the way to alternative way to compute the rate.
Okay.
So instead of like going to the figure and analyzing slope, you have a saving plan.
Sure. Okay.
I believe it is really great to have this backup thing. Now, can you try to download the orbital module from the last email I was sending? Like download and save to your.
Okay.
Okay. Okay. Now let's. Very good. Very good. Let's go to the command line. Just click inside. Lower. Below the. Let's go to the. Yes. Click. Type ls. Enter.
LS.
ls. Yes, for list. Enter. And it should have this module orbital ED. So let's just type module orbital right here. Module orbital underscore EV underscore A. Okay. Enter. So
I have a graph, but
can you please bring this graph?
okay, let me try to.
Right now you're sharing only MATLAB script and the command line. And if you bring this new graph that did pop up,
Can you see it now?
yes. So it is absolutely perfect. There is a big science behind it. So
Okay.
you may consider, if your time allows, to do it after after each of your MATLAB runs. Maybe it will be too much, but at least for some critical cases. So if your field equals 0, right?
Yep.
Reference point. But let's not do any calculations. Let's just analyze what you have right now. So the colored lines are eigenstates of electron in this potential, right?
Okay.
So the lowest one is blue.
Yep.
And it is located in the leftmost segment of this honeycomb. So there is a potential with dips corresponding to individual atoms, right?
Mm-hmm.
And there is a blue eigenstate that is localized on the leftmost atom, right?
Yeah.
Then the next one, orange, is localized in the next atom. It has a little bit higher energy, but the peak is localized at the second atom from the left.
Yep.
Now, if we look to the area that corresponds to approximately 25 angstrom, we will see there an eigenstate. It will be like number, you can point it with marker. Eigens upper, higher, 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 more, two more. And now to the right. To the right. Yes. And down. Right and down. Yeah, here. So in this first atom of the acceptor material, there is another eigenstate. Right?
Okay.
So there are two segments. You are considering interface between two materials. One is electron donor on the left and electron acceptor on the right.
Okay.
Basically, your research is computations in support of simplest element of the circuit, the diode. And your result will support the activity of a diode. So in one way, it will go more vividly. In other way, it will work as a gate. So right now, we do see that the state that you're pointing in the next one to the left from it, do not overlap in energy and space, and they have quite high energy. So the next in space is about 5 electron volt higher. So if you go up at point x equals 20, and you go higher up, approximately here. Yes, this one. So to go from the to this peak from the previous one we considered, one needs to have noticeable energy, and it is not energetically favorable. So right now, this what you're showing is a regime of closed gate dipole. If you swap the sign of the electric field and run the main code and then run this one, then the energy offset between peaks that you were considering will be much less, which will mean that gate is open and current can flow from donor side to acceptor side. These eigenstate images are not the main result of your research, but it is an important illustration that you can add when analyzing results.
Okay.
So I'm speaking too much. I'm talking too much. Do you have any questions about practical implementation of your practical work for your project?
I think I'm okay for right now after that, but
okay.
Yeah.
Okay, and send me a note if you need anything.
Okay, sounds good.
Okay.
Thank you.
Thank you. You may stop sharing.
Did I stop?
Yeah, it's fine. You did stop. Connor, would you consider to? Let me check if you can share. Okay, Connor, if you can consider to enable your microphone and sharing screen. Yeah. So I'm going to invite you to use the eigenstates later, but first let me ask if you observe any difficulties, or if you need any, if you're able to generate data in productive mode, and
I just want, so in one of the previous lab sessions you talked about the efficiency of the cell, of the solar cell. Is that just the transfer of electrons in the cell? And so it's just a product of the changing momentum, initial momentum?
Yes.
Okay.
So what you are doing right now is only one potential. It will be like one experiment, one sample. And if engineers try to design new solar cell, they do multiple samples, and they will have slightly different potential, and then they compare rates between different samples.
Okay. And then I just had in here on this what's I just wanted to know what's the difference between this orange and blue line.
They are computed by method 2 and method 3.
Okay.
And method 3 is more reliable, so one of them is a little bit better.
Okay. Is that the orange one? Is the orange one method?
Which one is made by method 3? Then you answer your own question. I do not know it from the top of the head.
Okay.
And let's just go immediately to the very end and see for plotting comments. So yes, probably the very last plot time 1 AVPL2, plot time 1 AVPRPL3. So you may you need the one that is PL3 and PR3. And in order to make sure, you may just delete everything related to PL2 or let me finish just in case. If you are not comfortable deleting, just then at the very place before the bracket in this line 340, before the last bracket, before closing bracket, do comma, please type comma, apostrophe, like quotes, yes, apostrophe, dot dash, or just dash, yeah, right, dash, and close another apostrophe. Yep. And instead of rewriting the whole code, you can just copy this line and paste it into the command line. Copy the whole line. Copy. Now go to yes and paste. And now show what figure. No, it's maybe a different one. Let's do.
Nope, that didn't change anything.
Type figure and figure, enter, and now arrow up, enter. Do you see which one is dashed? Or it is
no, neither of them are dashed.
Okay, let's go back to command line. Arrow up, do dash, and then K, letter K. No, arrow up, back, like yes, letter K, enter. So the lowest, the one became.
Oh yeah.
Yes. So this one is correct. The one that gives.
Okay.
Overall.
Okay.
So if you do not have any emergent questions, let's try to plot orbitals.
Okay.
Download the download it.
There we go.
In the command line, type ls. Please type pwd. Enter. Okay, so it is DOS0D, and maybe it's fine. Just click on the triangle run to run this new script. Okay, Very good, very good. So I think for your case, it's really outstanding. So can you just tell how you interpret this figure?
So this is the die, this indent here, and then these are the eigenstates.
Mm-hmm.
Um, why? I just have a quick question. Why are these three eigenstates? Why are there peaks on these three eigenstates and none of the other ones for the die?
So
Uh,
the die is quite confined, right?
yes.
And the stronger the confinement, the less eigenstates belong to this object,
Okay.
which is quite natural for molecular objects like dice. There are discrete homo-lumo levels, and that's it. For
Okay.
semiconductor objects, where a lot of atoms are closely spaced, the states are more dense and form like bands. There are much more states. So
Okay.
in this image, there are 3 states localized on die and about 15 states localized on the semiconductor, right?
Mhm.
So the um, if one starts the dynamics from one of the eigenstates, it will not change in time. But if you start from the eigenstate with added momentum, then the state may overcome the barrier and transfer from left to the right.
Okay.
And the best transition will be between such states which have the minimal energy offset. So there is a purple state for lowest state on a die, and at the same energy, there is a blue line. Yes, this one. That is the closest eigenstate of the semiconductor.
Okay.
In some sense, there should be possible transition between these two, and your simulation illustrates it. Some researchers avoid doing dynamics and just explore eigenstates and make some conclusions out of it. But in your research is more powerful because you are looking explicitly how transfer is going on. So if you just add this image at the beginning before you start going over the details, it may help readers to understand specifics of your system.
Okay.
Whew. So if any of you plan to ask questions today or during this night, which I plan to look for emails and answer, do not hesitate to send me the version of the code that you are running. If you want me to run, like right now, we are sharing screen and I suggest to type something, but if you will be offline, I will need a copy of the code so I can inspect it and make some suggestions. Yes?
So for the
Uh-huh.
on here,
Just a second, Zain, let me check with Connor because he's already sharing screen.
you're all good.
So Connor, do you have any open questions that needs to be answered, or you are fine for production?
Not right now. I could use just a quick brush over on how to export a moving plot, but that's not
Just
immediately
repeat.
necessary.
Just repeat.
Just like a quick run over of how to produce a moving plot, like export this plot when it's like originally moving.
Okay. The simplest and quickest way, maybe not the most beautiful, but the quickest, is just to do screen capture. And
Okay.
Jared was suggesting some that PowerPoint has insert image when it allows to select the area, right? Connor, do you understand what?
Yeah, I can get this, but I want the moving when it's actually moving, the movie.
Oh, okay. You want to save the movie.
Yeah.
Okay. Let's please send me this version of the code. I will answer some emergent questions in the class, and then I will just make sure it is running and then send it back.
Okay, thank you.
Okay, so you may stop sharing. There are some questions in the face-to-face part of the class, and I will return back to the seat and ask for other emergent questions. Wait into the camera.
So this lead cluster, how is that? Do I need to show an image of that? Because I'm guessing the lead is going to be the donor acceptor pair for going from 2+ to 3+, or is it the lead bromine sharing the electron between the bromine and the lead?
I understand the question and I look at the answer. I'll just take a few seconds to put. If you read literature on the Malthus theory, it was originally designed for charge transfer between wide isolated objects, which can be described as donor and acceptor. But the same theory will work for less localized when there is a change of point of state associated with charge transfer inside one molecule, inside one object, inside one cluster. So the only critical thing is that there are potential surfaces which are offset, and they could be offset by quite small number. So in the situation shown here, the offset is this fraction of the answer. So one without loss of generality, without any shortcomings in explaining Malthus theory, I need to declare what is the specific focus of this object. So it is same as Spencer is doing. So it's following the middle, which means it is not charge conserved. One state when it's neutral, and another when electron is removed, ionized. Okay, so it is charge transfer basically between your object and the rest of the world. So your molecule is dominant, and the rest of the world is accepted.
Okay. And this cluster, are we saying there's 1 lead, 6 bromine in this cluster, or do we balance that
out? It is balanced to have the neutral charge when it is neutral before we charge it.
Okay, so it's some sort of. So this is kind of a cluster.
Mm-hmm.
Okay, so we do have the 3 bromine.
So three. There are 3 extra, 4 extra bromines, right?
Yes, there are 4 extra bromines.
So each bromine is minus, right?
Yeah.
So in order to make it stable, it should be like lead bromine 6.
So
4 minus, right?
yes. So it would be 6.
Yes.
Okay.
And the calculation for them for octahedral geometry, right?
Okay. Yep. So it has these. So it's kind of like or is light going to be connected to all of them?
Light is going to be connected to all the points.
Perfect. Thank you.
Yeah. Thank you. Thank you for doing it. You explain and understand things much quicker than I can express or draw it myself.
Okay.
Yes.
Question on how to modify the MATLAB code. So I'm trying to get a nice value of dB, like the variable that you say, and so then I let all of this. This was all hidden. So I showed that, and then I said dB equals to v2 minus v1. Right? That's what we want. So we can compare it to this. And then
You don't need to do anything with this.
I don't.
No. Let's just keep the same protocol. Let's maybe if you share the screen,
Okay.
you're in a more comfortable environment.
And once I do that, it gives me a bunch of values.
No. Let's scroll through the beginning. Let me make a little declaration and announcement. The code was updated from year to year, and it has some noise and garbage that is not used for current run. It's just a try.
So did I hide this stuff then?
Well, you can hide or you can keep it. It will not affect the results the most. Let's scroll to the beginning. Let's go to the beginning of the code. It should start with reading, yes, PES load PS-PO. So this is most important. This is most important. And then your potential will be expressed in terms of this potential energy surface. So let's slowly scroll further. No, not as quick. Let's go back. And so no, let me focus on it. So second is energy in EV. E underscore EV is PES. Now I'm going to look for. We should look together for this. Yes, for this variable being used for next time. You can either scroll or just find. Yes, use this find E underscore EV. Okay, E capital. Yes, it was very quick. Now let's find where E capital is used for anything. Next after this. Let's just keep going. Maybe just let's scroll, but not as quick. Yes, very good. Now let's slowly. So E, scroll further. Scroll further. Keep scrolling in the space. Yeah, keep scrolling. It will be soon. It will be soon when we need to stop it. Keep going. I'm looking for the definition of Hamiltonian. Interesting. Let's. Oh, okay. It is here. Stop further. M2, M3, V. M3, V. So we need to find M3. Yes. Yes, but we need to find before. No, where the V is defined. Not M3 we found it, but where V is defined. We need to find how the V capital is defined in terms of the E.
So the up or down?
Up. I'm looking for like V equals E capital. Oh, stop. V equals YY. Line 81. Very good. Okay, now we need to find where is YY. I think it was so strange way because of several steps of debugging. Spline. Okay, okay, very good. Yes, yes, we found it. So line 73 defines y equals e, and yy equals spline x, y, x, x. Very good. So the potential that you are using is stored in this in all these variables e, y, v. The spline is used because the data that you are reading, potential energy surface data you are reading from the file are quite sparse, right? There are maybe like 40 points. And for quantum dynamics to work reliably, one needs to have like several hundred points as an area of definition. So one uses the spline, fills the gaps by interpolation formula, and uses and develops continuous potential as function of your coordinate, of your reaction coordinate. But if you need to find the barrier energy, we can do it just by plotting V and analyzing it. Yep. Yeah, click here, Control C and type figure, enter, plot V. Good. Okay. So in atomic units, your barrier energy will be 0.02. Yeah, from this point to the beginning of 0. And you can, if you want more exact number, in command line, you can type max, comma, V, at uppercase V. So 0.0199. And if you need the same number in electron volts, you can type max E underscore EV. In capital underscore underscore close bracket. Okay. Upper line arrow up, one arrow yes minus, type minus E underscore EV underscore EV, open bracket, number one, close bracket. Enter. So about 5.55 electron volts. So it's like maybe a quarter of the photon energy, and it is substantially bigger than thermal. Thermal energy is 0.03 electron volts. So it's like several thousand Kelvin. Okay. And then when you rerun the code with different values of momentum and process data, you should obtain this the activation energy smaller than this number. I believe it will be something like 0.2 of what you are going to obtain in electron volts. And the atomic units, the conversion is 27. Okay. I am available for any questions.
Why is the mass of the cluster like 56,000 rather than 600?
Can you share screen?
Yeah, just log on to Zoom real quick.
Yeah, and I'll make you a co-host. Not yet. Yes, I see you. Okay.
So in this, we have the mass. I'll multiply all these together.
Okay. So first, everyone has a right for the error, including whoever was writing the code. But assuming that it is correct,
Is the star multiplied?
so let's without equal sign, just mess.
Yeah.
Okay. Let's type 1837. No, in command line. 1837 multiply 12. Enter. Okay. So it would be the mass corresponding to a carbon atom. So the proton is factor between proton and electron is 1837. And now you just look for in the periodic table for atomic mass of bromine. Or it's like
So 6 bromine plus lead is 687.
okay. 687.
I'm guessing 12.
What is 19 times 12? Can you just type? You can type it in MATLAB in command line. It works.
28.
228. it's a little strange for me. I would do 1837 by 687.
1837 times 687.
Yes. But you can explore this ambiguity of the masses and report it, because if you find that you use the wrong mass and have arguments for it, you need to redo everything. Okay, so just use this and tell that the question of setting mass of normal mode has some open questions. Also, there is a thing that we didn't touch in this class, but there is a concept of reduced mass. It's not my design; it's standard thing. For example, if you find vibrational frequency of hydrogen chloride, or one makes an analogy with ball on a spring, with the mass of the ball will be somewhere between mass of hydrogen and mass of the chloride. And there is an equation for making this for computing this reduced mass. Basically, it's product of this mass is divided by this summation.
Is this the molecule?
Yes. Yes.
Or is it the fourth
one? The lead is 2 plus.
2 plus?
Yes. And then 2. Yeah. Did you find it available for purchase by Sigma Aldrich? Or
No, they don't even have there's no reactions.
Well, I think to stabilize it, one needs 4 cations, for monocations, or just some cations to stabilize it in the liquid.
So could you use CZ or something?
Yes, exactly. And if you mention it, it's right on the sharp edge of the modern science, because when it goes from solvent into solid, between this octahedral units stabilized by cesium cation, it makes a solid that makes record high conversion of solar energy into electric power. So best solar cells are made out of this stuff, stabilized by cesium, and then it grows as a solid. Okay. So let me check. I'm available for questions. With Connor, Kennedy, and Jared, or Zane, questions, feel free to. Yes, I do have a couple of meetings, but they are not, how to say, high impact. I just need to show my face and smile back, and people will be talking. So I will be like a student on a lecture. Not efficient student on a lecture. Just declaring my presence, but not doing things. So send me anything tonight, tomorrow. I'll try to answering your questions will be a priority of the day. Awesome. So, do you think we need to discuss anything else, or we are ready for departure?
I got one.
Okay. Yeah. If you want to use time and equipment to complete things here, please do. If you want, I can sit here and this. If you don't, it's fine.
Should be good.
Good, good.
So it's a redox reaction between the lead-bromine complex and the environment.
Yes. And this statement will be correct only for the initial offset.
Yep.
Any other offsets are hypothetical. We do not know which mode will it correspond to.
Actually,
Yes.
so I did my one or ln of my reaction rate, and I got this graph, and just doesn't look right.
No, it should be like this, but
Opposite, so upside down.
What rate is? Well, this point is the biggest, so it should be 5.
Yep. So yeah, that's my only of the reaction rates up here. Do I need to do 1 over the energy offset?
No,
Nope, just leave the energy offset. So
it's great. Thank you. You do.
and it's weird that reaction rate is highest on 0, since 1 will have technically where it intersects the derivative of 0. This one doesn't have the highest reaction. 0 value.
So it is your research observation, which can be rationalized. So the Marcus theory is designed for Marcus parabolas combine multiple normal modes of several frequencies. And it's typically considered in the limit when temperature is bigger than the vibrational frequency.
Okay, so since I'm keeping my temperature constant,
and since you use low temperature,
yeah.
Since nature for this problem, the frequency of this vibrations is quite high, you have signature of quantum effects.
Okay.
So if well, for you there is no time to do, but if there would be like 20 people in the class, we could do someone else running similar things with smaller vibration frequency or bigger temperature, then it will be less and less quantum features and it will be more and more stable.
Okay. And then for my figures in my research paper, if I did this and made this a figure, this would be one figure, that'd be good.
Let me share something for everyone, or maybe I'll instruct you with that. Okay. So if you share screen, there is a little thing which is very quick to do. Maybe I'll do it myself. Screen. Okay. So taking some figure, and then there is an arrow, and it slightly differs from version to version. So I double click, and then it opens a panel that controls properties of the figure. So if I click in the gray area and do double click, right, then it shows figure color, and I can change it from gray to white. It will look much better. If I click on this axis, it brings up this font. I can increase it which will make a figure much more beautiful. And if I type like x-axis, there is a way to change labels right in the code, but if it is too late, you can just click on the property editor and type like position and then it appears here. There is also like save as. One can export and select the type of the figure like JPEG or PDF, and then it will be it's not a better quality than just printing screen, but sometimes it is needed. And some of you may want, I don't know, it is more for true publication, but one may want to increase the size, the thickness of the line. So if one clicks on the line, one can make it thicker, and then it appears more noticeable.